Yeah, so like to tell you about lines in three-dimensional space. So here in blue and red, you see some lines that meet in various ways. And in this talk, there will be no physics at all until the very, very end. I think on slide 26 or 27, I'll say something about physics. But whenever I say line in three space, for those who know, you can think about momentum twister or bitwister. But for everybody else, I'm going to talk about lines in three-dimensional space. So the lecture is based on a recent paper called Varieties of Lines in Three Space with Ben Hollering, Elia, and Matteo. Here's the team, and here we're acting out the configuration of 5 lines in the plane. You see a little picture on the blackboard. Those is, of course, a bicolored triangulation, exactly like in Melissa's talk. And so I'll tell you in this lecture how lines in three space can intersect or not. Right? That's what the topic is, so I think this can be appreciated by everybody. But of course, along the way, I'll inflict some algebra words on you and again. How can lines in three space intersect? Well, first of all, how do we write down a line? So a line in three space for adults is written in terms of Plücker coordinates. So a line has a line A in three space, so three space is projective three space, has 6 coordinates, A12, A13 up to A34, the point in the Grassmannian, G24. As we've seen many times now, the Grassmannian is defined by this quadratic Plücker relation. But if you want to think about the line as being spanned by 2 points, then maybe you like to think about the line as the row span of a 2x4 matrix. Then the Plücker coordinate Aij is the 2x2 subdeterminant. It's the minor with column indices I and j. Now, the most basic question we can ask about 2 lines, A and B, is whether they intersect or not, right? And then algebraically, this can be written as follows. So if you have the matrices A and B, then you can stack them on top of each other. So you take a 2x4 matrix A, you put it on top of a 2x4 matrix B, and then that 4x4 determinant is 0 if and only if the lines meet. Right? So one line is spanned by 2 points, and the other line is spanned by 2 points. Then the 2 lines meet if and only if the 4 points lie in a plane. But of course, we want to use Plücker coordinates. And so in Plücker coordinates, this is the Laplace expansion, which we saw in the context of twistor coordinates yesterday. So this is the Laplace expansion with respect to the first 2 rows and last 2 rows. So it's this quadratic form in A and B. So this is the basic equation of this talk. This vanishes if and only if the lines A and B meet. Expression, I'll call that AB, if and only if they intersect. Now, what happens if the 2 lines, if A equals B? Right, so let's say here you substitute each B, you replace it by an A. Well, then what you get up to a factor of 2 is the Plücker relation. Right? The Plücker relation, which is an identity, simply records the fact that these are lines. Right? So it's automatically 0. Okay, so I like to talk about configurations of L lines in Pn. And so that's this configuration of L lines in Pn, that's a point in the product space, the Grassmannian times itself, L times. Now the number L here, that's already funny. This was the result of a negotiation with my co-authors, okay? So in math, we would think about n lines, right? We have n lines, so the natural letter to take would be a lowercase n, and my co-authors insisted that in physics this should be a capital L. So mathematician wanted lowercase n, and physicists wanted capital L, and then the compromise was this /ELL. Okay? So the reason why we're using L lines is because of this negotiation. All right, so we're going to study subvarieties that are defined by these equations. That's all. So for the next hour, that's what we're going to do. Well, I have it in, so each Grassmannian is in its own P5. So it's a subvariety of P5 times P5 times P5 L times. I want to do this Grassmannian to the L is a subvariety in a product of projective spaces P5 times P5 times P5. And I have a whole bunch of, I have these Plücker relations, of course, that just says we're in the Grassmannian. And then for some pairs of lines, I have this A-B relation. Okay. I told you it's going to get easier, right? Okay, let's talk about 3 lines, right? So, okay. So for 3 lines, we have this ambient space, P1 times P1 times P5, P5 times P5, Hayayush, that's a 15-dimensional ambient space. And then each of these contains a Grassmannian. So this product of these Grassmannians is a 12-dimensional variety. Very nice 12-dimensional manifold. And now to speak about this algebraically, we're using a polynomial ring in 18 variables. And the variables are A12, A13, up to C34. Okay? And the field C here is the complex numbers to make you feel good. Right? That's really, of course, the rational numbers in any computation. Okay, so the first thing we do, well, let's maybe look at pairwise intersecting triples. So let's look at 3 lines such that any pair intersects. Right? So we go to our computer, right? And we're going to look at the equations AB, AC, and BC. And just to recap, AB means this. Right? And now I have 3 of those for A and B, A and C, and B and C. And I tacitly assume that the Plücker relations hold. Now, what do? You go to your computer algebra system and you say primary decomposition. Right? You want to know what is the solution set, and asking for the solution set means computing the primary decomposition. In the olden days, this was done purely symbolically, but it's 2026, right? So we also have numerical tools to do bigger examples. But this is easy, you know. You type this into Macaulay 2, and you find that this is already not prime, it's radical, and it's the intersection of 2 prime ideals, which I call I3 and I3 dual. So prime ideals represent irreducible varieties, and the first prime ideal represents triples of concurrent lines. So concurrent means that these are lines that go through a common point. I have lines in 3 space, I have 3 of them that go through one and the same point. But then there's a dual situation, and that's why I call this star. So these are triples of coplanar lines. Right? The other possibility is that you have 3 lines that lie in a common plane. And these are really distinct irreducible varieties, and they intersect, right? So this intersection of ideals is the union of varieties, and then and these 2 components intersect, well, in little star pictures, like triples of coplanar concurrent lines. Now, one nice thing about this example is this has been studied before, right? So there was a paper from almost 10 years ago with Jean Ponce and Matthew Traeger, 2 computer scientists working in computer vision. And we wrote a paper called Congruences and Concurrent Lines in Multi-View Geometry. Okay. Well, who studies lines in 3 space? A lot of people study lines in 3 space, but in particular, people in computer vision study lines in 3 space, and that's because light travels along lines. If you take a picture with the camera, then, you know, your image, you know, comes to my camera through a straight line. So, representation of 3-dimensional scenes by 2-dimensional images called photographs, and more importantly, the recover of 3-dimensional structures from 2-dimensional images is all about lines. And here, this is the subject in computer science is called multi-view geometry, and we analyzed, you know, these concurrent lines, and this ideal has 10 additional cubic generators. So it has these quadrics that we know. But then to generate the prime ideal, there are some cubics, and those cubics are determinants of certain 3 by 3 matrices, and this was studied in this paper. So this is a nice subject, actually. So nowadays, of course, like everything in science and engineering, it's all like AI, right? But it's a very, very nice subject. So back then, around 10 years ago, there was a very famous paper called How to Build Rome in One Day, right? And so that people uploaded, so people travel to Rome, tourists, and they take pictures of the Colosseum and everything else, right? And then there's an automatic process how to reconstruct Rome as a 3D model. And that's all called multi-view geometry, and you could imagine that lines sort of play a role. So what I'm saying, if you are a physicist and you think about momentum twisters, the knowledge that you have with or without doing integrals could be very useful for the rest of the world. So there's the rest of the world out there, well beyond periods and pure mathematics. There are applied people, and they can and will benefit from your knowledge about topics like lines in 3 space. Okay, let's talk a little bit about 4 lines. So 4 lines is a bit more interesting than 3 lines, right? So let's take G, fixing a graph. So now the graph in a moment will tell us which lines are incident and not. So I'm saying we have L equals 4 lines, and the graph has 5 edges. So I'm prescribing 5 of the 6 incidences. So if the lines are called A, B, C, D, then my ideal is generated by AB, AC, AD, BC, and BD. Now this ideal is again radical, but it now is the intersection of 4 prime ideals. And Melissa gets progressively more happy, right? They're exactly her pictures. And so now we're subdividing a square into black and white triangles. And this corresponds to here the corresponding pictures of lines. And here are the prime ideals. So this ideal is the intersection of 1, 2, 3, 4 prime ideals. So let's start here. So this I, 1, 2, 3, 4, this is the concurrent lines variety. So this is quadruples of lines all going through one point. And that's a prime ideal, and here's the picture. I have 4 lines in 3 space, they go through a common point. Here the entirely white triangle means that I have 4 lines that lie in a common plane. But then more interesting are these 2 mixed situations. So here, for example, this black triangle 1, 2, 3 means that 1, 2, and 3 are concurrent, and 1, 3, and 4 are coplanar, and here's the other one. So here 1, 2, and 3 are coplanar, and 1, 3, and 4 are concurrent. And you can act this out with your friends. Sticks, or in the Asian restaurant with chopsticks, you can act out each of these irreducible varieties. Okay, please interrupt me with questions. So this variety is also a complete intersection, right? So I have 5 equations inside my ambient quadruple Grassmannian, right? There's an ambient 16-dimensional variety. It very happily lives in P5 times P5 times P5 times P5, which is 20-dimensional. But inside this, it has codimension 5. So there's an 11-dimensional variety, and as I already told you the secret that Elia is very good in figuring out these kind of dimensions, right? So this is an 11-dimensional variety. It's a complete intersection, and each of these components has the same dimension 11. Okay, so complete intersection means the number of equations, each equation cuts down 1 dimension. It's a complete intersection, and complete intersection implies Cohen-Macaulay. I know you don't like words like Cohen-Macaulay, but you talk long enough to Felix, you might actually like it. So these are names of people. Yes, question. Oh, the graph is the graph on 4 vertices with edges 1, 2, 1, 3, 1, 4, 2, 3, and 3, 4. I'm going to give you the formal definition. The graph just tells me which pair of lines is supposed to be incident. Okay, the example clear? So you can do this on your own. You can think about a bunch of lines and say, in this case, there are 4 scenarios, and those are the irreducible components. Let's define this. So if we have L lines, we introduce the polynomial ring in 6 L Plücker variables. So each of the L lines has 6 Plücker coordinates. And then we always throw in the equations AI. This is just the Plücker relation, the ith Plücker relation. This cuts out this 4L-dimensional variety in this 5L-dimensional ambient space. So now you see G is a graph. So you're fixing a graph on L vertices. So this is an undirected simple graph. So I simply represent it by the edges. Right? So these are undirected pairs. So I tell you for each pair ij if the lines are supposed to meet. And then the ideal I look at the ideal generated by my quadratic equations Aj whenever ij is an edge in the graph. Okay. Now this ideal defines a variety, and I call this the incidence variety. The incidence variety Vg is the zero set of this ideal, and this is a subvariety in this L-fold Grassmannian, and therefore in this L-fold product of P5s. Yes? No, that's up to you. All I'm saying is, I'm not making any statement about 2 or 4. 2 or 4 may or may not intersect. Right? They're allowed not to intersect, but if they want to intersect, that's their problem. Right? So here, of course, on this component they intersect, and here typically they don't intersect. But they may or may not intersect. So the rule is the graph just tells you those pairs must intersect, and the other pairs can do whatever they want to do. Okay, other questions? Do I have multiplicity? Yeah, okay, that's a scheme. Okay, we're going to get there. Okay, so I said variety, but it's actually a scheme. Okay, it is a scheme, right? So Ig need not be a radical ideal. So we have interesting embedded multiplicity structure. And we see this already for the complete graph with 4 vertices. So now if I have 4 lines, and I take the 6 equations that says any 2 of them are supposed to meet, then I call this ideal IK4. K4 is the complete graph on 4 vertices. And that's the intersection of the concurrent prime ideal, happily studied in computer vision, and the coplanar prime ideal, dual to it. But then there is an embedded component. Right? There's an embedded on the geometric intersection. There is a non-reduced structure. So there is a primary ideal. So I take this and I throw in the sum of the squares of the 2 others. So this is an embedded primary ideal. These are 3 associated primes, 2 minimal primes, and 1 embedded prime. And that's the way it is. That's, how that if you give equations, right, that could be multiplicity and embedded structure, and that is important. Okay, so this need not be a radical ideal. Now here's the one that Dani was asking about. So the strict realizations form a subvariety WG. So Vg is the variety I started with, but let's look at the points inside the variety where the ij that are non-edges actually don't meet. Right? So, and then that's not closed, right? And then I take this Zariski closure, and that I'm going to call Wg. So Wg is the subvariety, it's a Zariski closure of all strict realizations of the graph. So in this example here, all of this is Vg, but then only these 2 components are in Wg. Now, Wg can be empty. Could happen that Wg is empty, so let's take this little wheel graph. So if I have 6 lines and they look like this, so 5 form a ring and 1 is incident to all the others, then, well, the Vg always has dimension 2L plus G. Well, 2L plus 3, that's the dimension for the complete graph, right? I have a concurrence to concurrent lines. That's 2L plus 3 dimensional, and every Vg contains the V for the complete graph. So therefore, every VG, no matter what the graph is non-empty and has fairly large dimension, but WG might be empty, okay? So it's an incidence theorem. You can check that if you have 6 lines and you require precisely these 10 incidences and none other, you can't do it, right? So these 10 incidences will force at least one other incidence. It could happen that the strict realization variety WG is empty, but we're mostly interested in this VG, and that's always non-empty. Okay. Here's another example, just to kind of see that this gets interesting and complicated. It involves the W again. Let's take this graph. This is a graph with 5 vertices and 7 edges. So here in my notation, I have these 7 edges. So 4 and 5 are the ones down here, and 1, 2, and 3 are the others. So this is the complete bipartite graph K, 2, 3 with 1 more edge thrown in. Now, this ideal is not a radical ideal. However, it is a complete intersection, right? So it's a complete intersection of codimension 7, right? There's 7 equations, and this has codimension 7 in this 20-dimensional ambient space. So there's a 13-dimensional variety cut out by the right number of equations. And here is a primary decomposition. So here I can use the definite article, right? So when you study primary decomposition, and you should study primary decomposition, for example, from my nonlinear algebra book, and you should study primary decomposition, especially if you are a PhD student in Bonn in physics and interested in the leading terms of series expansions, of Feynman integrals and all that, then you better study a little bit of primary decomposition, because when I talk about multiplicity and schemes and all that, that's the log factors. Right? So in the leading term, you see stuff, right? And whenever there's a log, that means there's some multiplicity going on. So when I say primary and I use these words, it's words that are good for you to speak about leading terms in your series expansion in the presence of logarithms. All right. Okay, so here's a primary decomposition. This is unique because it's a complete intersection. They all have the same dimension. And here are 8 familiar ideals. So this is all, everybody's concurrent, everybody's coplanar. And here I have this bicolored mixing, right? So here 1, 2, 4, and 5 are coplanar, and this is concurrent and coplanar. But then there's an interesting component 9. So this ideal Q is a primary ideal, but it's not prime. What's interesting about this example is the radical of Q is actually WG. The WG is the strict realization variety. It's here. So all of these are not strict. So if you go through this list and you look at what they mean, each of these 8 components has an undesired edge, a non-edge, becoming also collinear. And what is this? Well, you take the same. So what is W? So you take 4 and 5 to be the same line, and arbitrary lines 1, 2, and 3 that intersect that double line. This doesn't sound like a strict realization, but it is actually a strict realization. So again, you take 4 and 5, you make them the same line. Particularly, they intersect, and then you pick 3 lines at random that intersect that chunky line. That is a strict realization, and this has this non-reduced scheme structure. So the conclusion is the main component, the entire component, has a non-reduced double structure. So not only do we see the multiplicities on embedded components, we see it on the top dimension, in fact, the strict realization component. Okay. Now, it's always good, I told you when a variety walks into the door and we agreed what your dimension is, the second question is to look at the degree. Again, the degree is your friend, right? It helps you to keep track of organizing the combinatorics, right? So each of these things has a degree, and they add up correctly, and it has to be 2 to the 7, because I have 7 quadratic equations, and that's Bézout's theorem. So if you're missing a component, then counting degrees will tell you. Okay, here's an example with 5 lines. Okay, well, geometry is in your head, right? But how do you communicate all of this to the computer? So I'll tell you a little bit what we use for symbolic computation, and then I'll tell you a little bit about numerical computation, and then we'll get back to some pretty geometry. I'm typing this. So this is at the limit of what Macaulay 2 can do. The computer, you type this into, you don't have to type much. I mean, you go A, B, A, C, right? You type this in, and there's a package, right? I think we have, I don't know, do we have Zenodo or something? The Ben Hollering has a package, very convenient. You just tell us what the edges are, and then the program says primary decomposition, and it comes back. Now, of course, this works for 4 and 5 lines. So as soon as you have 6 lines, eventually this is, 5 lines when a polynomial ring in 30 variables. Right? Already 30 Plücker coordinates. So that's why on the next slide, I'll tell you a little bit how to make this a bit more efficient. But this is the result of a computation. Now, of course, once you understand the structure and you know about Playback graphs and everything, then you can help the system along a little bit and input, things you know. But if you don't know anything, right, you just type in these equations and this comes back. Okay, now a bit more efficient calculation is with affine coordinates, and this is what physicists would have done in the first place. So I take my lines A, B, C, and I take a 2x4 matrix that has a 2x2 unit matrix on the left. So without loss of generality, I'm assuming that a rank 2 2x4 matrix looks like this. Right? And then now I have 4 honest parameters, alpha 1 to alpha 4 for the first line, and the betas for the second line, gammas for the third line, and so on. Right? So this now the Grassmannian manifestly has dimension 4. Now what about the incidence relation? So now in these coordinates, my A, B, as I said, you take 2 of these matrices, you stack them on top of each other, and you take the determinant, and this can be written like this. So this is an expression that's quadratic, and you can write this as follows. So the incidence of line A and line B, you take this little 2x2 matrix minus that 2x2 matrix, and you take its determinant. Right? So turns out the 4x4 stacked determinant simplifies to this little 2x2 determinant. And that's a more convenient affine way. So now you can try this. Now the following computation will be very quick. Right? You take the K3, the complete graph, so A, B, C, A, C, B, C, twiddle, right? And it turns out the primary decomposition is quite nice. So here you take for the first component, this is the concurrent component. Here you take alpha minus beta matrix, and then alpha minus gamma matrix, and that matrix has rank 1. And on the dual one, on the coplanar one, you take alpha minus beta transpose, and here you take alpha minus gamma transpose. So you take these difference matrices and you stack them next to each other for one component, and you stack their transposes for the other component. Now there is a proposition that requires a proof that says you're not losing any information. Well, why is that important? Well, because now we're working on an affine space, right? So we have P5 times P5 times P5, and inside each P5, we're choosing an affine chart. We're violently ripping out a hyperplane at infinity from each P5, and since there are many P5s, we're ripping out a lot of stuff, right? And this proposition says this ripping out doesn't harm the computation. This says the true primary decomposition upstairs of the true ideal in Plücker coordinates can be found by homogenizing, that is multi-homogenizing, this affine ideal IG twiddle. So IG twiddle is the ideal of all of these twiddle equations. And what this proposition says, you're not losing information by doing this. You can work in affine coordinates, break everything into components, embedded things, and so on, and then homogenize afterwards. This is true for any graph. And the reason it's true is because I have a group action, right? So because this property of lines being intersecting is a geometric property, and therefore, I can move my hyperplane infinity around. and it's this equivariance that gives rise to this proposition. So this proposition says, so here we're saying this is faster, and this is much faster, and I'm telling you in a moment another version that's even faster. Okay. Now, even faster is the following variant. We call this the spanning tree coordinate. So this we found to be the best way for symbolic computation. And it goes like this. So let's fix a graph G on 1 up to L. And let's assume it's connected. I have a connected graph on L vertices. And I pick a spanning tree T. And for each edge in the spanning tree, I introduce a 2 by 2 matrix XE of unknowns. So forget everything I said so far. You have a connected graph G, fix a spanning tree T, and for each edge in the spanning tree, you introduce a 2 by 2 matrix of variables, different variables. Okay? Well, now the spanning tree, of course, has L minus 1 edges, vertices. So therefore, we're having a polynomial ring now in all of these matrix entries that has 4L minus 4 variables. Okay? Now let's look at all the determinants for every edge in the spanning tree. Well, they use distinct variables, so this is the world's simplest equation. Right? So along the spanning tree, you take all these 2 by 2 minors, and this is toric. Now, toric is another one of those adjectives that means very good. Okay? So toric means the equations are very friendly and everything is very fast. So this is a toric complete intersection. Okay, so now the graph itself is not a tree. Let's look at an edge that's in the graph but not in the spanning tree. And as you know, for example, from the second semantic polynomial or a million other contexts, that this graph, the tree plus this extra edge, has a unique cycle. And that unique cycle contains G and a subset of the edges from the tree. Right? So the extra edge plus some edges E1 to ER from the tree, they form a unique cycle. You have a spanning tree, you throw in an extra edge, there's a unique cycle, and then the corresponding matrix I call YG. So YG is the sum of all the matrices XEI over all edges from the spanning tree that participate in that unique cycle. Call that YG. Okay, so now let's look at, in this polynomial ring here, let's look at the ideal IGT. So this depends on the graph and on the spanning tree. So first of all, you throw in the 2 by 2 minors along the spanning tree, happily toric, but then you also throw in the determinants of these YG matrices for all other edges. By definition, the definition says that it depends on the choice of spanning tree, but then the proposition says it doesn't. Right? So the ideal IG tilde, the affine ideal from the previous slide, which according to the proposition faithfully represent what happens in projective space. So this ideal of the incidence variety is up to linear change of coordinates, exactly this ideal. This proposition says a posteriori it didn't actually depend on the choice of spanning tree. And this is what we found to be the most efficient for symbolic computation. So the true object, again, we're in Plücker coordinates, then we can use these affine coordinates, but it turns out that this formulation is the most efficient. Let's see one example. So for example, the cycle. Let's say we have a cycle. Hodge's paper, very popular to have like lines meeting up in a cycle. Okay, well, in a cycle, not so. You just remove any edge and you have a spanning tree. Okay, so the ideal is simply I have a L minus 1 2 by 2 matrices, and then the remaining edge is just the determinant of the sum of the others. That's my ideal. Right? So my ideal is I have a bunch of 2 by 2 matrices, I take their determinants, and I also take the determinant of the sum. And it turns out that this ideal is prime. Okay, so for a cycle, everything is nice. The complete graph, yes, Christian? we found that that doesn't influence the computation time. The combinatorics, sometimes if you have a nice, you want to choose a spanning tree that sort of makes the combinatorics nice, in the computation time it didn't make a difference. Okay, let's try the complete graph, right? So we already agreed that for the complete graph on 4 or more lines, the ideal is not radical. So let's check this, right? So IGT. So for example, for the complete graph, so I'm not going to use the blackboard, right? So for a complete graph, a good way to choose a spanning tree is to pick one vertex and connect it to everybody else. Right? That's a good choice of spanning tree in the complete graph. So if we do that, then we have, again, L matrices. We take their 2 by 2 determinants, and then we throw in the determinant for any sum of only 2. Right? So I have a bunch of 2 by 2 matrices, and for any pairwise sum, I also throw in the determinant. And then, as we know, this has 2 associated primes, and this is just like we've seen. So these are the 2 by 2 minors. So I take these 2 by 2 matrices, I stack them next to each other, and then here I stack the transposes. So this is the concurrent component, and this is the coplanar component in this formulation. Let's see a computer example. So I didn't even think of you, Melissa, when we did this, but now I think of you. So, okay, so let's take the hexagon, and let's triangulate the hexagon. Okay, and there is a spanning tree looking at you. So spanning tree is like this vertex connected to the others. So now let's use spanning tree coordinates. So this means there are 20 coordinates. That's 4 times L minus 1, 20 of these. I call these coordinates A. Okay, so I'm sorry. So so A1, B1, C1. Okay, so these are the matrices. So X1 is this 2 by 2 matrix with A1, B1, C1, D1. And then X2, and then X5. Right? So I'm introducing in Macaulay 2, I take 5 2 by 2 matrices with unknown entries that are called A and B and C and D. Okay? So then the ideal here is, so I always have to take the determinants, but then the way the combinatoric, so the non-spanning tree edges are the 4 out here, and that's the determinant of X1 plus X2, X1 plus X3, X3 plus X4, and so on. Okay, now this Betty Mingens, that's just for sanity, how many minimal generators did I type in, right? And then you do co-dim degree. A variety just walked onto the slide, right? First question is, what is your dimension? What is your degree, right? And then you want to solve the system, right? Let's decompose it. So decompose, and then toString just means print it, right? And then, checking, is this a radical ideal? And then the answer is yes, right? So this says true or false, so this comes back yes. And then this one tells us there are 16 associated primes, so it's a radical ideal. That means the ideal is an intersection of prime ideals, and there are 16 of them, and each of them has codimension 9. Francesca, in your opinion, what are those 16 associated primes? I know you paid attention in Melissa's talk. Were you at Melissa's talk yesterday? No. Were you? Anybody was at Melissa's talk? So what are those 16 associated primes in this example? Any opinions? Yeah. I mean, you see, there are 1, 2, 3, 4 triangles, right? You can maybe color each of them white or black. Right? Now, black means concurrent. White means collinear. That's it. In this example, it's a perfect match. Right? We get exactly this situation. And we're still trying to understand this a little bit better for other graphs. So my co-author Matteo sends many notes. He sent me another note yesterday, and so I pressed him a little bit on these positroidal varieties and vector relation configurations. What's exactly, and we're slowly learning this. So when I'm saying this is really dual to Melissa, this is not something that sort of came down with Moses from the mount. This is something we're learning right now. Right? We're right now trying to understand exactly, what is the precise relationship between these structures and the structures we see in Playback graphs and positron. All right, very good. So, Dani to the rescue. The 16 components are the bicolorings. Now, a new topic. This is a topic Ayush has been waiting for. He came all the way from Linz in Oberösterreich to listen to this. So this is the Elikesh Sharia framework. And okay, these are people in computational geometry. And we found this very nice paper by Reed Raz called Configurations of Lines in Space and Combinatorial Rigidity. So space is 3 space, and combinatorial rigidity, I tell you what it is. And Orit, she's a professor at the Hebrew University in Jerusalem. And this was published 9 years ago. Okay? So here's what we do. We're going to identify 4-dimensional space with R22. Okay? Now, to me, R22 is the space of pairs of points in the plane, in the Euclidean plane. So for now, when I write R22, I mean the 4-dimensional space where each element is a pair of points, one point in the plane and another point in the plane. And I just call it R22. Might as well. Okay, so such a pair might be ST. So when I write ST, that means I have a point S in the plane with coordinates S1 and S2, and a second point, T, with coordinates T1 and T2. Now, if I have 2 elements in here, could they call them ST and UV? And now what we're going to do is we're going to make a linear change of coordinates like this. So I'm going to replace the S's and T's, which there are 4, by alpha 1, alpha 2, alpha 3, and alpha 4 like this. I'm performing this linear change of coordinates. And then on, beta, I'll do the same, right? So beta, I introduce the same. And now with this change of coordinates, alpha minus beta are the spanning tree coordinates from 12 minutes ago. Make this precise, right? Namely, the equation that the lines A, B are incident. So the inner product of A and B in Plücker coordinates or stacked 4x4 determinants is equal to the equation that the Euclidean distance between S and U squared is equal to the Euclidean distance between T and V squared. There's a little compute. It looks weird, Zach, I know, but it's a little fact. Right? So this, if you know about points, okay. This is the distance, right? The squared Euclidean distance between S and U in the plane. And if you take this expression minus that expression and you perform this change of coordinates, then you get the equations for the line A and B being incident. No. The lines are in 3 space. Remember, alpha, beta, those were the tree coordinates. Okay, here they are. Okay, here we have, or maybe this, let's say the affine coordinates, right? So 3 was the differences. So here is alpha, beta, these are 4 coordinates, manifestly 4 coordinates for the line A, and then the betas for the B, right? And now I'm saying the line A intersects the line B. Well, if this expression is 0, and you check that this expression, okay, is equal to this expression. This was observed by people in computational geometry. So computational geometry is a serious subject. It's between math and computer. Computer science is another one of those subjects that your knowledge of physics can contribute. Right, that's the equation. So let's phrase this as a lemma. So the Grassmannian G24, this 4-dimensional variety, is naturally a compactification of real 4-dimensional space, using all these rules. And for 2 point pairs here, the 2 Euclidean distances agree if and only if the corresponding lines intersect. That's what this equation says. So if I have a point in the Grassmannian and Nicholas has a point in the Grassmannian, if I have a line and you have a line, then I take my line and I write it as 2 points in the plane. And, he takes his line and also writes it at 2 points in the plane. And if the distance between our first coordinate point equals the distance of our second coordinate point, that's if and only if the lines meet. Elementary, you can prove this in high school, in math circles. Depending where you grew up, you join the math circle, you can do this in your math circle. Okay, now this brings us to rigidity theory, and all questions you will ask about rigidity theory, Ayush will be very happy to answer in the coffee break. So here, what we're going to do, now we're going to do this with L of them. So R2L is the space of configurations S of L points. Let me write R2L for configurations of L points in the Euclidean plane. And I have a graph now, and I'm going to record pairwise distances according to the graph. I have a distance measurement function, delta G, that takes L points in the plane and records in a long vector the squared distance for any pair of points. And I'm going way too slow. Now, rigidity theory studies the image and the fibers of this map. What we're saying is I have points in the plane, and for some pairs, I prescribe the distance. That's the fiber. Right? And the image is what are the possible pairs of distances you can have, right, for points in the plane. And that study is called rigidity theory. And that's a very big subject. For example, there's a very nice forthcoming undergraduate textbook by Jessica Sidman and collaborator called Framework in Motions, an Introduction to Rigidity. And many people study this, right? There are special semesters in Linz and everywhere. Okay? Very good. And the dimension of the image is the rigidity rank of G. So this map, delta G, the image is an algebraic variety. It's also called the Cayley-Menger variety. I already advertised Cayley. Menger, of course, famously a professor in Vienna 100 years ago. So Menger and Schoenberg introduced a lot of this rigidity theory in Vienna 100 years ago. In any case, the rigidity rank is the dimension of this variety. Now, this variety, being the image of a polynomial map, is an irreducible variety. It's an irreducible variety in a space whose coordinates are indexed by the edges of my graph. Now, this irreducible variety, like every irreducible variety, determines an algebraic matroid. And that's called the rigidity matroid. We'll get there. But first of all, our incidence variety, so our incidence variety, Vg, in these coordinates, is simply the set of all pairs St. So now in this 4 L-dimensional space, 4 copies, L copies of R22. And that have the same image. So if you take this lemma, right, and this lemma immediately gives this proposition. So our variety in this formulation is simply pairs of configurations that have the same distance image, according to the graph. The graph does the measurement. You're measuring pairwise distances in the plane, and that is our variety. Delta is the measurement map. I have L points in the plane, and for every edge in the graph, I measure the squared Euclidean distance between point I and point J, and that's a number. And I make the tuple out of those numbers. Those are non-negative numbers, but there's a risky closure is a variety, and it's called the Cayley-Menger variety sometimes. All right, here's the matroid. So here I'm going to state the matroid as a matrix. Sometimes people come to me and say, how can I learn about matroids? It's complicated, You don't need to learn about matroids because you already know about matrices. Right? So if you have a matrix and you just remember what's sort of important about the matrix, then you have a matroid. Okay? So the Jacobian of this map, so for the complete graph. So let's do this on the complete graph. So I take the derivative of the delta map. So the Jacobian is a matrix of 2 L rows and 2 L choose 2 columns, one for each edge of the complete graph, and 2L because I have 2L coordinates for my points in the plane. Now this matrix has rank 2L minus 3, and the minus 3 is because I have Euclidean group acting on this, right? So if I have points in the plane and I move them around by rotations or translations, then the distances don't change. So I have the minus 3, this is simply the group of Euclidean motions in the plane. Okay, and this defines the rigidity matroid. So this is a matroid on L choose 2 elements of rank 2L minus 3, and it's studied by many people. One more, so I'm going to have some technical definitions. So I'm going to say a graph is AB sparse if for every non-empty subset of the vertices, the induced subgraph doesn't have too many edges, namely at most A times the number of vertices minus B. So this theorem, the Geiringer-Laman theorem, summarizes everything we need to know about the combinatorics of this situation. And it says the following: a graph G viewed as a subset of this matroid, so a subcollection of edges, is independent in the rigidity matroid if and only if it's 2,3 sparse in this definition. That's independent. Independent means there is no algebraic relation among those distances. If you make those measurements among pairwise distances in the plane, they're independent. There's no algebraic relation. Now the bases, the maximally independent sets in this matroid, can be constructed recursively as follows. You start with the complete graph on 2 vertices, 1 edge and 2 vertices, and you inductively do the following thing. You add 1 new vertex and you connect it to 2 old vertices. Or you subdivide an edge by a vertex and connect it to an old vertex. So each of these operations introduces 1 more vertex and 2 more edges. That's the 2s minus 3. And there's also 2 4 sparse. Let me spare you this. Who are these people, Geiringer and Laman? Laman was a mathematician in Amsterdam who proved this theorem in the 1970s. And it was known for a very long time as Laman's theorem, or Laman's matroid. And again, this is not a niche subject. This is something many people study. More people study this than D modules, by a margin. Okay, who is Geiringer? Geiringer was a PhD student in Vienna in the 1920s, working with the aforementioned Viennese, and nobody knew her work. Well, it was written in German, one of those strange languages I mentioned, but only fairly recently it was discovered that she had the same theorem. In a dissertation, Hilde Geiringer is now called the Geiringer-Laman theorem, and if you want to learn about, if you or your high school student nephew wants to learn about this, I recommend this undergraduate textbook. Rigid Menger. So Menger had this, so it was a subject called distance geometry. So distance geometry says, you have points, maybe in the plane or in 3 space, and you have partial information about the distances. To what extent can you reconstruct the structure, right? So this is important in architecture and in protein structure, drug design, right? This is important, right? You make pairwise measurements, and to what extent can you reconstruct the structure? Is it stable, right? Rigidity, you don't want the bridge to be collapsing, right? Would be good if it's a spanning set in the rigidity matroid. Okay, very good. So let's connect this to Melissa's lectures. Let's talk about the triangulation of the algon. So the triangulation of the algon in particular are bases in the rigidity matroid. So here is columns for L equals 4, 5, 6. And here I have some bases, right? So by this I mean, when you see a picture like this, take one of these graphs and label them by 1 up to L in any possible way. Right? Then you take the edges, and the number of edges is 2L minus 3. And that set of edges will be a basis. The bridge is minimally stable. There will be a basis in the rigidity matroid. Now these are circuits, right? So these are spanning circuits. So they have 1 more edge than a basis. So So for example, a K4, so these wheel graphs, they're always circuits in the matroid. They are minimally dependent. In other words, the Cayley-Menger variety of these things is a hypersurface. Right? So here, the Cayley-Menger variety, Sandra, fills the space, and here it's a hypersurface. Okay, so let's talk about the triangulations of the Algon. Right? So here they are, and that's our graph. Well then, VG has 2 to the L minus 2 irreducible components, each of the correct codimension, one for each bicoloring the triangles, and this is the rank of the Laman matroid. And this is the independent discovery, let's say, of bicolorings of the triangulations of the N-gon that one might look at for other reasons. Now, the wheel graph is also interesting. So the wheel graph is always a circuit, and it has fewer, it almost has the same. It has 2 to the L minus 1 minus 2 times L minus 1 irreducible components. So from rigidity theory and from the theorem that writes our variety VG, as pairs of points with the same image under the distance measure map, we get a lot of mileage. Okay, now come the painful slides. So I'm going to just flash these quickly, and then I come to the juicy part at the end. Okay, variety walks into the door. What is your dimension? Well, there's a theorem that gives you the dimension. And there's a little bit of fine print that I maybe spare you, right? And it's all expressed in terms of the rigidity matrix. So for example, if the variety is a complete intersection, and that's a case we like a lot, then the graph must be independent. And independent means it's a subgraph of a basis. So when we talk about these momentum twisters later in physics in 11 minutes, then subgraphs of these things are the ones we like best. Here's a theorem that gives the dimension. So for any graph, the codimension of VG is some combinatorial number having to do with ranks. This is rigidity rank. Rank here always means rigidity rank. So the rank of the Laman matroid and its minors drives the dimensions of all of these things. Okay, here's more painful definitions. I didn't know that I'm already speaking for an hour. I'm too slow. Anyway, a bunch of painful definitions, but then you can harvest some theorems, right? So this theorem says our incidence variety is a complete intersection if and only if some combinatorial condition hold. The graph is 2, 3 sparse, and it's contraction stable. That was defined on the previous slide. Then there's another theorem that says when the variety is irreducible, so the variety is irreducible if and only if the graph is 2, 4 sparse. That was another one of those conditions. And it's strictly contraction stable, right? In this case, VG is equal to WG. That's the component, that's the piece that Donnie likes. And this irreducible variety is a unirational complete intersection. So in this case, all of these pieces are actually unirational, not obvious. This one I like a lot. Right? So if you're in this context of these incidence varieties, if the variety is irreducible as a set, if it's irreducible, then the ideal is prime. It's weird, right? Because the converse holds always, right? If you have a prime ideal, then the variety is irreducible. The converse is very false, but in this context, it's true. So these are a bunch of nice theorems, all of which are derived using rigidity theory. I won't say invented, but let's say studied a lot by Geiringer and her advisors in the 1920s in Vienna. Since then, the action has moved from Vienna, from Lower Austria to Upper Austria, and Ayush will be very happy to tell you more in the coffee break. I have 2 more topics. One more is numerical computation, right? So we did a lot of computation. So if you have 6, 7, and 8 lines, then you really need homotopy continuation. And then we did a lot of computations. So we did a decomposition for all connected graphs up to 7 vertices. We did all triangle-free graphs up to 8 vertices. So we like the triangle-free graphs because those are the ones we don't understand. If there are lots of triangles, then we have Playback graphs and we know a lot of things. So the triangle-free graphs are the ones that are more mysterious. So we went up to 8, and there's lots of data. Why do we have data? Well, data keeps us honest, right? So the physicists call this mathematical data. So very, very good to have data because somebody else might be interested in lines in 3 space, right? Okay, maybe one word. I mean, you've seen this, and we have blue lines and red lines. So this suggests bipartite graphs. Maybe one slide on bipartite graphs. So L equals 8. So there are 267 triangle-free graphs on 8 vertices up to relabeling. 266 are realizable, and here by realizable I mean that they have a strict realization. But there's one that has W empty, and that's K44. So K44, that's the complete bipartite graph on 4 plus 4 vertices. And this variety you cannot do in Macaulay 2. Okay? So this variety you have to do numerically. So there are 63 irreducible components. They have various codimensions ranging from 13 to 15. But there's an incidence theorem, right? If you have 8 lines and you have the 16 incidences of the complete graph K44, then some other incidences must hold. And then there's a general theorem that for complete bipartite graph, really the rulings of the quadric tells the story. Okay, more data, histograms. Okay, a multi-degree. It takes a little getting used to, but if you have a subvariety in a product of projective spaces, the degree is not a number. The degree is a cohomology class. The degree is always a cohomology class, but in particular, it's a cohomology class. So it's an element. Here we're going to do the cohomology of the ambient P2, P5 to the L. So that's a polynomial ring in L formal variables, P1 to the S up to TL to the S. Now then, the cohomology class of VG is a homogeneous polynomial in these T's whose degree is the codimension. This is not scary at all because in Macaulay there is a one-line command called the multi-degree. So you go to Macaulay 2, you write down your variety, and then you say multi-degree, and then this comes back, right? Now, geometric interpretation is intersecting, right? So in an ordinary projective space, the degree is the number of intersection points with the linear space of complementary dimension. But in a product space, you have to take mix and match linear spaces from each P5. All right, so here's a theorem. So any particular coefficient, so I'm going to write gamma u for a coefficient here. I'm organizing the exponents like this. So this is the coefficient in this multi-degree, in this cohomology class. This is the so-called leading singularity degree, or LS degree, of an auxiliary graph, depending on u. So depending which coefficient you are, you make a new graph. And then this graph has a number called the LS degree, or leading singularity degree. Now, the earlier degree, of course, you can always go from the fine grading to a coarse grading, and this is the technical remark. So earlier I said 2 to the 7 was something, 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 and that's this summary. So what is GU, and what are leading singularities anyways, right? Well, you can do Schubert problems as follows. Let me write D for the dimension of the variety. So this is 4L minus the codimension in the product of Grassmannians. I'm fixing a vector U of coordinate sum D. So then I'm making a new graph, GU, from G by attaching UI edges at each vertex. So at each vertex, I'm attaching UI additional edges. You get these hairy pictures that have things sticking out that you already saw in Melissa's talk. Now then I have a map, psi u. So here we just called it psi u. Recently, Matteo calls this the Landau map. Okay, so it's Matteo. Okay, so the Landau map, psi u, takes the variety of GU. So this is the variety with those additional edges, down to the boundary measurement. So I'm going to the Grassmannian on D. So D are the external edges that I added. And that deletes the L original lines. Now the fibers of this map are given by D constraints on a D-dimensional variety, that is expected to have finitely many solutions, and each of these is a Schubert condition. Now, the number of solutions is the LS degree, or leading singularity degree, if it's finite, zero otherwise. That's a positive integer. It's a leading singularity degree. And Elia will be very happy to tell you in the coffee break what this has to do with Landau analysis and leading singularities. In the remaining 6 minutes, let's do one example. Okay, let's do L equals 1. I'm talking, Sandra, about the graph with one vertex and no edge. G has one vertex and no edge at all. Well, so then, you know, I'm just talking about the Grassmannian. Vg is the Grassmannian, right? The dimension is 4. So U1 is 4, okay? So then GU is simply this star tree, right? I have this one vertex, and I'm sticking 4, and I'm not allowed to write on the blackboard, right? So my body is this graph, and then, you know, I'm sticking 4 legs on it, 2 arms and 2 legs, okay? That's the graph. Now, what are the points? Okay, no quiz, right? I'll just tell you. So this is, you know, configurations of 5 lines, namely 4 exterior lines meeting the one central line. Now, the map, psi, lovingly called Landau map by Matteo, deletes the central line, and only the 4 free-floating lines stay around. Now, what's the fiber? The fiber is 2 lines that meet 4 given lines in P3. I'm given 4. This fiber is okay. Now, every conversation about Schubert calculus starts with 4 lines in P3, and we ask the question, how many lines are in? And the answer is 2. Okay, so the LS degree of this graph is 2. Not 1. Sorry. Melissa likes this to be 1. I'm happy with 2. Okay, well, you know, you can compute these multi-degrees. If it's a complete intersection, you just multiply in the cohomology ring. By the way, Alan Knudsen, not entirely unknown around here, and Laura Escobar followed up on our computer vision paper. So remember, in 2017, this was called computer vision. And I had asked the question, our paper, what is the cohomology class? And they figured this out. And so this is a nice story. Let's go back to the triangle. So for example, for the triangle, we know that this variety has 2 components, so the cohomology is additive. It's a complete intersection, right? So I have 8, T1, T2, T3, so this is for the 3 Grassmannians. And then this, I have the pairwise incidences. These are the bilinear relations. You multiply this out, and here, you know, you have the LS degree 8, and here you have the LS degree 16. And the quiz, if there were one, would be to explain these numbers, right? So what are the Schubert problems? Well, what am I saying, right? So I have this triangle, and maybe let's do this one, 3, 3, 3. I have this triangle, and on each vertex, I'm sticking 3 additional exterior lines, 3 additional legs. Right? Now that means, now I'm looking at the fiber. Now the Landau map maps us to those 9 lines at infinity. Well, the fibers are as follows. Given 9 general lines in 3 space, how many triples of lines are there that meet them according to this pattern and or pairwise intersect? And the answer is 16. Now, why would somebody study such a thing? Well, for example, Bojali, Vergu, and von Hippel in this paper in 2023 studied exactly this thing. And they drew the dual graph. So this is the dual graph to the one I just told you 28 seconds ago. Right? So here is for each of these pentagons, there's a line, a line, a line. Then outside, I have 9 regions. And then these incidences, so this says that this interior line here is incident to a line here and here and here. Okay, anyway, so this is really exactly this. And finally, with 2 minutes ago, sounds like physics. And I apologize for going over time. But let's talk about physics for 2 minutes. And this is for people who have never heard about physics. So let me try you, Claudia. You have heard about this is for you. Okay. Now we're going to reboot, and we're going to identify R4 with R13. That's Minkowski space. And we're going to perform a change of coordinates. We're going to replace our earlier 2x4 matrices. These are the 2x4 matrices that represent lines A and B. And I'm going to do this change of coordinates. I'm going to rate P to be this matrix and Q to be this matrix. I is the square root of -1. Now, why do we need the square root of -1? Because we're Wick rotating from signature 4 to signature 3,1. And that requires a square root of -1. Earlier in the rigidity discussion, we rotated from signature 4 to signature 2,2. And that did not require a square root of -1. But here, we need I. Now, the incidence relation becomes this, right? Now, stack this matrix on top of this matrix, take the determinant, and now this is the determinant. Okay, so this means I have two particles, P and Q, whose difference vector is on the light count. They are causally related. And there's Veronica. So lemma, the Grassmannian G24 is also a natural compactification of space-time, R13. Two particles are light-like separated, meaning this thing vanishes, if and only if the lines P and Q intersected. Okay? So in signature 2,2, we had the connection to rigidity and Hilde Geiringer. Right? Here we have the connection to Veronica and her light cone. Now this is very natural, right? Because the boundary of the light cone is a Schubert divisor in the Grassmannian. Right? So really you're taking the four-dimensional space around us and you're identifying it with an open piece in the four-dimensional Grassmannian. Yeah, this is the paper, section 8, okay? So for example, now the incidence variety parameterizes configurations of L particles where light-like separation is prescribed for pairs of particles at the edges in the graph. And this is written for Claudia. So it's like, what do people do at the Hadron Collider and so on and so on and so on. And this is a little discussion. Of course, this is completely trivial for the physicists, but it was completely new to me. That's the end of it, right? So the original motivation, this is from the introduction, for this project comes from particle physics. These varieties VG, and even more so important, VGU, are essential in the Landau analysis in terms of Grassmannian coordinates. And we're currently working on the physics paper called Landau Analysis in the Grassmannian. And what the previous page was supposed to be a friendly introduction for mathematicians. Thanks for listening.